So now, in this video, we're going to talk about something that's not terribly complicated, but it's a good thing to keep in mind when you're designing your own circuit. So most circuits you see the voltage is 5 volts. That is usually typical when you're looking at these simple circuits right there. It's a common voltage used to power simple circuits, but there's a lot of lithium iron phosphate batteries out there. And if you haven't invested a lot in electronics, but you got a lot of lithium iron phosphate batteries, you might want to power circuits with them. And so we're just going to light an LED. I'm not using a battery. I'm using the power supply just to simulate one. And because the battery voltage changes very slowly, I can change it instantly for the demonstration purpose. So red LED right there. We got 14.6 volts. So that would be what a lithium iron phosphate battery, the 12 volt version, it's 12.8 volt nominal, because half the time, if you use it fully, half the time it's a higher voltage than 12.8, half the time it's lower. But in any case, while the charger is applied, that's the voltage to force current into it. And then once you remove the charger, because it's fully charged, no more current is really trickling into it, then you got about 13.6 volts. And then as you use it, a little more than halfway, you got like 12.6. And I like to generally stop at 12 volts. You used almost all the charge, but you can squeeze out a little bit more. Get to 10 volts. You don't want to drop below 10 volts if you're using a 12 volt lithium iron phosphate battery, because the cells are at their minimum voltage, 2.5 volts. Below that, they start getting to the point where they can get damaged. And so you want to avoid that. Recharge basically as soon as you hit like 10 volts is recommended. So in any case, and you can always stop sooner. So you can see the red LED still, it's not quite a fireball looking thing, but it's still decently bright right there, even at somewhere around like 8 milliamps of current. So we're just going to end that when it comes to showing what the circuit does at the different voltages. If we're using a lithium iron phosphate battery, this setup is probably going to keep a red LED decently bright at all times. Now we have the 2 series resistors, because we could use a 940 ohm resistor, make things simple, just a 1000 ohm resistor, close enough. But in any case, we could use a 940 ohm resistor, a single one, but these are quarter watt resistors. You can see the size. That's the most common size that you buy. Generally, if you just buy resistors, that's the size they'll come in, quarter watt, unless you actually look for like half watt or something or whatever. But you probably already got a whole bunch of quarter watt resistors. So you want to use them in circuits as much as you can. And this isn't like super high voltage where we got to take a lot of precautions. But it's somewhat high, because normally you wire a red LED with 5 volts, or at least most schematics are that way. So instead of a lone one, we got 2 of them in series. So what that does, it splits up the voltage that's going to be across them. So now let's look at that. We have up to 14.6 volts, because the main thing is we have to worry about is the maximum voltage. We want to make sure we don't put too much current through our load, and then that includes the resistors. But when it comes to the resistors, the voltage is fixed, about 2 volts across the LED, and the rest of the voltage is divided up by the resistors right there. So if you got about 14.6 volts right there, I wrote in the notes the 2 volt drop of the LED. So 2 of those volts go across the red LED. So that maximum voltage, now we got a total of 12.6 volts and our total resistance right there. So this isn't what we're going to use for the wattage now, because that total voltage is not across each component but both of them. And about 13.4 milliamps of current. Do the math in amps. So each one of the resistors, since they're in series, they drop, or they split up the voltage. They divide it. And so out of that 12.6 volts, if they're perfectly equal value right there, because it is based on the total percentage of resistance. So we're going to say they're perfectly equal. Out of that 12.6 volts, each one of the resistors will have 6.3 volts across them. And that's when you do the wattage calculation. So the current's flowing through all 4 of these components equally. That's how current goes when things are in series. 6.3 volts across each resistor times 0.0134 amps going through the entire circuit equals 0.084 watts. So quarter watt resistor is 0.25, but you still want to stay below half of that. So 0.125. That's a fair amount below 0.125. I can actually touch these resistors when I get to about 0.125 watts. Usually they kind of burn. They are getting warm, especially if I hold them for a while. But, you know, it didn't hurt at all to hold that. But I wouldn't hold it very long. So, any case, when I yank them out and I know that they've been to 0.125 watts approximately, it kind of hurts to pull them out. But these small ones don't cause severe burns. You know, it kind of hurts, but, you know, then it's over with. Large resistors will hurt you. Don't touch them when they're being powered, the large resistors. But in any case, that's what we got. If we just use a 940 ohm resistor, it would have the full voltage across it, 12.6 volts. So current would be the same in this particular circuit if you used one 940 instead of the two 470 in series. So yeah, this is simple. It'd just be twice as much wattage. So that's 0.168 watts right there, which is quite a bit above 0.125 watts. So probably won't be catastrophic. You know, the resistor probably might not ever get damaged, you know, but still, that's really hot. Better to stay about halfway below. But the main thing with this circuit is that you get an idea that you can simply take more resistors in series that are lower value resistors for a total of a higher value resistance in order to split up the heat that they generate. So now, those of you that like multimeter measurements, don't know how many that might be, but it might help if you see the measurements anyways. This is an hour ranging meter. All I have to do is set it to V for voltage. I haven't filmed this yet, and so we still got 10 volts at the supply. We can look at those voltages as well right there. And so, of course, you know, for safety, you look at the maximum voltage and make sure the minimum voltage still works okay. But there you can see, basically 2 volts across there. So we got 10 volts total. That'll be 8 volts across these two resistors, but each resistor will have about 4 volts across it right there. So it won't be perfectly the same because each one of them has slightly different resistance and whatever. But there you can see, it's really simple. Put resistors in series and they split up the voltage based on how much resistance each one has. They get the percentage of resistance, or the percentage of voltage across them, that they are the percentage of resistance. So we got about 14.6 volts, and that is lower than what we calculated. So we can look at the current coming up. So in any case, we can see how much is making it to the rail. So it's going to fall a little bit short because there is resistances in the wire and stuff. And so we got about 2 volts across the LED. It's going to be a little bit higher because as more current flows through an LED, its forward voltage builds up a little bit. So yeah, we calculated about 6.3. Again, these won't be exact numbers across each one of them. So that's the total across the two of them, and each one of them has about half of the total voltage across them right there. Pretty straightforward. So as I said before, we can measure the current. So I don't want to set the meter to measure current until we are ready to do so. And yeah, the resistor was quite hot and not super hot. We have to make a gap somewhere in the circuit. Doesn't matter where. So it's easier to move that resistor than that jumper. We have this little gap. No current flowing right now. When it comes to series components, as long as they're in series, they have the same current flowing through them. And all I gotta do, set it to milliamps. If there's a number, it's very important that you set it to a number higher than what it can measure. And I think this has an upper limit of 600 milliamps of current that it can measure at this setting. So I almost knocked something over. So yeah, we're going to bridge the gap right there. And yeah, there you can see about 13.5 milliamps of current is flowing through. Pretty close to what we calculated right there. As we said before, we're losing a little bit of voltage along the way. But yeah, there you can see I just lost connection. And then I accidentally multimeter probe slipped and we got something else. But yeah, there you can see power supply not as accurate as the multimeter right there. So always something to keep in mind if you are using a power supply to kind of estimate how much current's flowing. So I'm just bridging the gap between those two resistors there. And before I slipped and came down here, So I think I went through one resistor in the LED for a little bit. One reason why I use these alligator clips attached to these jumpers there. I can clip it to the probe, and then it's really easy for me to set in the board. It's very rare I slip and make a wrong connection. We have the multimeter set to measure current. As I said before, if you cover this, it thinks it's dark enough that it lights the backlight. I really like this meter, but they don't really sell it. But yeah, we just measure current. It's very important. I get it off of measuring current. So if I'm still going to use it, maybe I'll set it to V for voltage, but of course, since there's not like a power on-off button, might as well just turn it to off right there until you're ready to use it. But definitely get off measuring current. If you try to measure more current than what the setting is, there's fuses in here, and those fuses will blow. You got to replace the fuse. In fact, I'm pretty sure I have to replace the high current fuse. So, in any case, this video is pretty long, but I hope you still enjoyed. Thanks for watching. Make sure you check out one of the other videos I posted on the screen, and check out links down below. They help out a lot. I'll see you in the next video.